Good morning, students. So last class, a few topics in chemical bonding completed. Hydrogen bonding also completed. Next is, and one more important concept is MOED. This is a molecular orbital. Here there is a molecular orbital energy level diagram. Here electronic configuration is important. So up to N2, we follow this electronic configuration. Sigma 1s2, we know that these are the bonding orbitals, and sigma 1s2 anti-bonding. Next, the sigma 2s2 bonding, sigma 2s2 anti-bonding. Next, pi 2px, that is equal energy with pi 2p by pi anti-bonding 2px is equal to pi anti-bonding 2p by. Next is, after this, sigma 2s2 anti-bonding, pi anti-bonding with 2p by sigma 2pz anti-bonding. So this is electronic configuration up to nitrogen molecule. Up to 14 electrons, we follow this electronic configuration. So nitrogen, what is it here? Total electrons are 7 plus 7, that is equal to 14. Here 2, 2, 4, 6, 8, 10, 12, 14. So from this we can find out the bond order. Bond order is equal to half into bonding electrons minus anti-bonding electrons. So that is equal to half into how many bonding electrons? 2, 4, 6, 8, 10 bonding electrons and 4 anti-bonding electrons. So we get a 3. If you get a negative value, that molecule is not exist. Any molecule, if bond order we get a negative value, that molecule existence is not possible. That is unstable molecule. If you get a fractional also, that is not not stable. So bond order is a positive value that indicates that molecule is more stable in nature. And from oxygen molecule, from oxygen we follow this order, sigma 1s. Okay, oxygen total electrons are 16. So from 16 electrons we follow this order, sigma 1s2, sigma 1s2 with anti-bonding, sigma 2s2, sigma 2s2 with anti-bonding. Next, sigma 2pz. Next, pi 2px, pi 2py, and pi anti-bonding with 2px, pi anti-bonding with 2py, sigma 2pz anti-bonding. This is electronic configuration. And here 16 electrons, 1s2, 1s, sigma 1s2 anti-bonding, sigma 2s2 bonding, sigma 2s2 anti-bonding. Here 2 to 4, 6, 8, 10, 11, 12, 13, 14, 15, 16. Two unpaired electrons are present. So O2 is the paramagnetic in nature, and bond order is equal to half into bonding electrons 10, anti-bonding electrons 6, that is equal to we get 2. So from 16 electrons we follow this order. And this molecular orbital electronic configuration explains the molecule is stable or unstable. It is a paramagnetic or diamagnetic, and magnetic nature also explained. So this in chemical bonding, now we discuss few questions the previous entrance exams. Here few species are given. O2, first one O2, second one SO3, third one CO3 minus 2, next SO2. Okay, identify species having one pi bond and maximum number of canonical forms. maximum number of canonical or resonance forms. Show that which compound shows in these molecules, which compound shows the maximum number of canonical forms, or we can call it as a resonance forms. Once again, for resonance, which conditions are required? Pi bond is in conjugation with pi bond. Pi bond is in conjugation with negative charge. Pi bond is in conjugation with positive charge. Pi bond with unpaired electron, lone pair of electrons. Pi bond with unpaired of electron. If these conditions are present, then that molecule shows resonance. Okay, that molecule shows resonance. O2 molecule. O2 molecule. So here canonical form is not possible. SO3 also. Here resonance is not possible. But in SO2 also, no conjugation. But the CO3 minus 2, O minus. In this case, resonance structures are possible. How many resonance structures are possible? Number of resonance structures always equal to number of conjugated positions. Here, pi bond is in conjugation with negative charge. Pi bond is in conjugation with negative charge. 3 conjugated positions are there. 3 resonating structures are possible. So this pi electrons transfer to this side. This electron is transferred to this. Canonical forms are indicated by double-headed arrow mark. Canonical forms also called resonating structures. O minus, double bond. Again, this is transferred. Again, this is transferred. These electrons enter here. What is the next structure? O minus, double bond O minus. So, how many canonical forms are possible? 3 canonical forms are possible because the number of conjugated positions are 3. Next is calculate dipole moments of CCl4, CHCl3, CH4 in order. Question is, write dipole moments, increasing or decreasing order of dipole moments in this order. So we know that if any molecule shows a dipole moment, okay. So there are 2 possibilities are there. Mu is equal to 0, mu not equal to 0. Mu is equal to 0, dipole moment is 0. This is also called non-polar, and this is also called polar. What is the condition for polar? What is the condition for polar? Okay, central atom here. Central atom contains lone pair electrons. That is always polar. Here, surrounding atoms different. It is also polar in nature. Non-polar, no lone pairs at the central atom. Surrounding atoms are same. If these conditions are followed, then that molecule is called as a non-polar molecule. In a given molecule CCl4, find out in CCl4 how many lone pair electrons are present at the central atom CCl4. Okay. CCl4, Cl. We know one formula also. Bond pairs is equal to 4 into valency 1, 4. And we find out lone pairs is equal to group number of central atom 4 minus bond pairs by 2, 0. So CCl4 is non-polar in nature. So mu is equal to 0. The same way CH4 also, mu is equal to 0, but CHCl3 surrounding atoms are different, so it shows a dipole moment. So, what is the order of dipole moment? CHCl3 greater than CCl4, that is equal to CH4. And one more question. Here 4 molecules are given. NO2. Second is NO2, NH2. Third is NO2, NH2. Fourth is NO2, NH2. Here, 4 molecules are given. Which molecule dipole moment is maximum? So dipole moment is a vector quantity, we know that. NO2 withdrawing group. So it shows the dipole moment, nitrobenzene, but that is the direction of the dipole moment. And second compound, para position, amine group is there. Amine group contains a lone pair at the central atom. So amine group is a donating group. NO2 also donating group. NO2 withdrawing group. So direction is in one side only. Here, this is the direction. This is the direction. In this case, this is direction of dipole moment. From this, where dipole moment is maximum, in this case, B, dipole moment is maximum. Next question. One more question here about that dipole moment. Chlorobenzene, para dichlorobenzene. Here at para positions, 2 cyano groups are there. Again at para position, 2 OH groups are present. OH groups. One more compound, para group SH is present. So question is, in which molecule mu not equal to 0? Here, this is this direction, it is in this direction, mu is equal to 0. Cyanide also withdrawing group, this is the direction, mu is equal to 0. But in case of OH, central atom oxygen shows a lone pair of electron. So if lone pair is present, what happened? It shows a dipole moment. The same way SH also, central atom shows what is that, lone pair electrons. So in this case, mu is not equal to 0. In this case, mu is not equal to 0. Both cases, mu is not equal to 0. So first 2 cases, dipole moment is equal to 0. Next 2 cases, dipole moment is not equal to 0. Next question. F is Cl2, A is Cl3, S is Cl2, Mg is Cl2. So question is, which of the following molecule shows maximum covalent character? So here few conditions are there. For maximum covalent nature, we follow Clausen's rule, ionic nature, low charge, one condition of cation and anion indicates ionic nature, and covalent nature, more charge. of cation anion indicates covalent nature. More charge of cation anion indicates the covalent nature. In these molecules, Fe charge is +2, AlCl3 aluminum charge is +3, Sn +2, Mg +2. So AlCl3 positive charge is more. So it shows more covalency, more covalent nature. Next question. When Born-Haber cycle is given, KCl is given. Born-Haber cycle of KCl is given. Questions from Born-Haber cycle also. KCl Born-Haber cycle is given. Enthalpy of formation of for KCl is equal to minus 436.7 kilojoules per mole. Enthalpy of sublimation for K is equal to 89.2 kilojoules per mole. Enthalpy of ionization for chlorine is equal to, for potassium is equal to 419 kilojoules per mole. Enthalpy of electron affinity of Cl for Cl is equal to minus 348.6 kilojoules per mole. And bond dissociation enthalpy of Cl2 is 234 kilojoules per mole. Calculate lattice enthalpy. What is lattice enthalpy? Calculate. Okay. So generally it is a, what is that? It is related to, what is that? Tesla. What is enthalpy of formation? Here, potassium and chlorine both are combined to form potassium chloride. That in a one-step enthalpy of formation, reaction takes place. That is enthalpy of formation. Okay, in a multi-step process, first potassium solid is converted into potassium gas. For this, some energy is required. That is called as a sublimation enthalpy. This process. Next, potassium gas loses electron and forms an ion. Ionization energy is required, and Cl2 dissociated into Cl. This is a bond dissociation enthalpy is required. Okay, but one Cl only there, so we write here Cl2 into Cl, half Cl2 into Cl, half of bond dissociation enthalpy is required. Cl again gains electron, it forms a -1. This is the exothermic process. Sublimation enthalpy is endothermic process. Ionization is endothermic process. Bond dissociation is endothermic process. Formation of Cl minus exothermic. Na plus, sorry, K plus gaseous state, Cl minus in gaseous state, 1 mole combined to form KCl. And here energy evolved is called lattice enthalpy. Lattice enthalpy is exothermic. So here enthalpy of formation is equal to sublimation enthalpy, enthalpy of sublimation plus enthalpy of ionization or ionization enthalpy plus half into bond dissociation enthalpy minus electron affinity because it is exothermic minus lattice enthalpy. So if we know all these values now. We know all these values. From that we can find out that lattice enthalpy, what is the formation enthalpy? Minus 436. Here we write formation enthalpy is the minus 436.7 is equal to sublimation enthalpy is 89.2 plus ionization is 419 kilojoules and electron affinity is minus 348. Bond dissociation enthalpy is equal to plus 234 by 2 minus lattice enthalpy. From this, we can calculate the lattice enthalpy of KCl. Okay. This is also an important question from chemical bonding. This question based on Born-Haber cycle. Next question is, find out hybridization in NO-1, NO2 -1, NO2 +1, NH4 +1. This is a question now. So we use one formula to find out hybridization of these molecules. What is the X value you find out? In case of this, X is equal to, in case of this, nitrogen is 5th group, oxygen 6th group, 2 oxygens are present too. On negative charge, we write +1. This is for NO2 -1. Okay. So 6 plus 12 is equal to 18, and it is divided with 8. 18, 8 2 is 16. 2, it indicates a lone pair. The denominator indicates a lone pair. Divided with 2 again, we get even number only. What is the number we get added here? We get 3 value, that is the sp2 hybridization, NO2 -1. The same way, NO2 +1. What is X value you find out? Nitrogen 5, oxygen 6, plus 6, plus 1 means you -1 you write here. 6, 6, 12 plus 4. Here 5 plus 6, 6, 12, 17. 17 minus 1 is equal to 16. Divided with 8. 8 2 is 16. Hybridization is Sp. NH4 +1. Nitrogen is 5th group. 4 hydrogens, group number 1. +1 indicates -1. 8 we get. We get 8 or less than 8 divided with 2. 2 4 is 8. What is hybridization? Sp3. So this is one method, simple method to find out hybridization of any molecule. Next question. Structure of IF7, one question here. Structure of IF7. So you find out the lone pairs and bond pairs in IF7. Bond pairs is equal to 7 into valency 1, 7. Lone pairs is equal to 7 minus 7 by 2. You get 0. So group number of central atom minus bond pairs by 2. You get 0. 7 bond pairs, sp3 d3 hybridization. What is the structure of the molecule? Pentagonal bipyramidal structure. Pentagonal bipyramidal structure. Next, one more compound. The compound has the largest MH bond angle. Okay, what is this? H2O, NH3, H2S, CH4. Here, what is the bond angle here? H2O, oxygen. This is the structure. 2 lone pairs and 2 bond pairs. You know how to find out the lone pairs. In H2O, find out the bond pairs. 2 surrounding atoms, hydrogens. Valency bond is equal to 2. Lone pairs, oxygen, group number 6 minus 2 bond pairs. By 2, we get 2 lone pairs. So ammonia, 1 lone pair. Three bond pairs, H2S. S again, same shape, two lone pairs and two bond pairs. CH4 tetrahedral shape. CH4 tetrahedral shape. So this oxide is the central atom. Two lone pairs are present. Bond angle is 104 degrees. Expected bond angle is 109 degrees. But because of two lone pairs, it shows a bond angle 104 degrees. Okay. In H2S, the central atom, same, two lone pairs and two bond pairs are present. If central atom electronegativity is less, then bond angle always decreases. So this bond angle is less than H2O. Ammonia pyramidal shape, one lone pair, bond angle is 107 degrees. CH4 no lone pair, bond angle is 109 degrees. So where bond angle is maximum, CH4 bond angle is maximum. One more question here. BF3, let's find out the shapes of molecule. BF3, NF3, ASF5, H2O. Okay, BF3. Find out the bond pairs and the lone pairs in BF3. Bond pairs is equal to three surrounding atoms. Chlorines balanced with 1, 3. Lone pairs is equal to central atom boron, 38 group, 3 minus 3 by 2, 0. In NF3, bond pairs is equal to same 3. Lone pairs is equal to nitrogen fifth group, 5 minus 3 by 2, 1 lone pair. ASF5, fifth group, bond pairs is equal to 5. Lone pairs is equal to arsenic fifth group, 5 minus 5 by 2 is equal to 0. H2O, lone pairs is equal to 2, bond pairs is equal to 2. Then what is the shape of BF3? 3 bond pairs only. It is a non-polar and it is a bent shape of molecule. It is a trigonal planar. Trigonal planar. NF3, one lone pair and 3 bond pairs are present. What is the shape? Pyramidal shape. H2O, V shape or bent shape. And ASF5, 5 bond pairs, no lone pairs. Structure is trigonal bipyramidal. Trigonal bipyramidal structure. This is a way to find out structure of a molecule. Next question. O2 minus 1 is given. One question, previous question. Find out bond order and magnetic moment. Magnetic moment. Question is find out the bond order and magnetic moment. Calculate. Then you write a first molecular orbital electronic configuration. So oxygen total 8,008 electrons and 8 electrons present with one negative charge. 17 electrons. Then we follow oxygen electronic configuration. Sigma 1s2, sigma 1s2 antibonding, sigma 2s2, sigma 2s2 antibonding. Next, sigma 2pz, 2, pi 2px, 2, pi 2p by 2. Next, pi antibonding 2px is equal to pi antibonding 2py. Here, how many electrons are filled? 2, 2, 4, 6, 8, 10, 12, 14, 15, 16, 17. So this is the electronic configuration of O2 minus 1. And only 1 ampere electron is present. How to find out magnetic moment? Mu is equal to root n into n plus 2. With the Bohr magnetons, n is equal to number of unpaired electrons. If 1 unpaired electron is present, 1.8, general approximate magnetic moment. 2 unpaired electrons 2.8, 3 unpaired 3.8, 4 unpaired 4.9, 5 unpaired it is a 5.8 or 9. You can find out simple way. What is the magnetic moment? That is a 1.8 and it is a paramagnetic in nature. So this is the way to find out magnetic moment and it is a paramagnetic or diamagnetic. So this is the questions. These are the questions in chemical bonding. Few important questions. And next concept is after chemical bonding. Next concept is we'll start with the polymers. Next important concept is polymers. What is the polymer? We know that many molecules are combined to form a macromolecular bigger molecule that is called as a polymer. So based on source, polymers are divided into 3 types. Classification of polymers, today's topic. Based on source, polymers are divided into 3 types. Availability, source or availability. Natural polymers, synthetic polymers, Third one is called as a semi-synthetic polymers. Okay. So what is this natural polymers? Generally, polymers are macromolecules which contains the main element is carbon again. This natural polymers are obtained from plants, animals. Okay, plants example sucrose, animals example. What is the example for animals? Proteins. Proteins are polymers of amino acids. Synthetic polymers, polythene. These are obtained from byproducts of petroleum. Semi-synthetic polymers. What is that? It is prepared from biopolymers, but it is obtained naturally. From that biopolymers, semi-synthetic polymers are prepared. Okay, natural polymers, semi-synthetic polymers are prepared. So, example nitrocellulose. An example nitrocellulose. These are prepared from natural polymers in labs. This is based on source: natural, synthetic, semi-synthetic polymers. Next, based on monomer units. Polymers are divided into 2 types. Homopolymers. Next is called as a copolymers. So in homopolymers, what is the same type of monomer units are present? Example polythene. N number of ethene molecule combined at high temperature, high pressure in presence of oxygen phases. What is this? Polythene is formed. And what is the nature of this polythene? It contains only one type of monomer units. This type of polymers are called as a homopolymers. Copolymers contains more than one type of monomer units. Example, bakelite. What is that contains? Bakelite contains 2 monomer units, phenol and formaldehyde. So this phenol and formaldehyde, these all are involved in polymerization process, phenol and formaldehyde, and in 3-dimensional way we get a bakelite polymer. So bakelite polymer is example for copolymer. So what is meaning of copolymer? If monomer units are different, more than one type of monomer unit is present, that is called as a copolymer. If same type of monomer units are present, that is called as a homopolymer. Next, based on preparation method. Based on preparation method, polymers are divided into two types. First is the condensation polymers. First one is condensation polymers. Condensation polymers. First one. Second is addition polymers. Condensation polymers and second one is called as a addition polymers. What is this condensation polymers? To take one example, bakelite. Okay, what is this bakelite? Or we take example nylon 66, hexamethylene diamine, N number involved in polymerization with adipic acid, CH2,4COOH. Here also COOH, N number of molecules. Here H2O is separated out, H2O separated, and we get this polymer NH, CH2, 6, NH, CO, CH2, 4, CO. How many molecules involved here? N number of molecules involved in this polymerization process. So, in any polymerization process, polymer is formed by losing of any molecule from that both monomer units. That type of polymerization is called as a condensation. That is called as a condensation polymerization. Okay. Next is addition polymerization. Addition polymerization. In addition polymerization, we take example polyethylene. How polyethylene is obtained? N number of ethene molecules form a polyethylene. Here, no molecule is separated from monomer units. So, this type of polymerization is called as a addition polymerization. Okay. Based on next classification, arrangement of monomer units. Arrangement of monomer units. Polymers are divided into linear polymers, branched chain polymers, and the third one is called as a cross-linked polymers. Three types are there. Based on arrangement of monomer units, linear polymers, branched chain polymers, and cross-linked polymers. In linear polymers, monomers are arranged like this. One monomer is arranged on other monomer. This is a close arrangement. Because of this close arrangement, these polymers are, what is the nature? Rigid with the high melting points, boiling points. Branched chain polymers. In monomer units, branches are present. These are called as a branched chain polymers. Okay. This is not a proper arrangement. It is irregular arrangement. What is example here? Nylon is an example. Okay. Because of this irregular arrangement, they have low melting points and boiling points. Example, rubber, natural rubber is example for branched chain polymer. In cross-linked polymer, Monomers are arranged in a proper way. Branches also arranged in a proper way. This is arrangement of branches. So these cross-linked polymers arrangement is three-dimensional. Arrangement is proper. So they show they are rigid, high melting point, boiling point are there. Example, bakelite. Example is bakelite. So based on arrangement of monomer units, polymers are divided into three types: linear, branched chain, cross-linked. Cross-linked also called as a three-dimensional polymers. Based on attractive forces between monomer units, polymers are divided into four types. What type of attractive force is generally present? Generally in between polymers, monomer units, dipole-dipole attractions are possible. Van der Waals force is also possible. Hydrogen bonds also possible. Disulfide bonds also possible. So this type of attractions are possible in between monomer units. Based on these attractive forces, polymers are divided into elastomers, fibers, thermoplastics, thermosetting plastics. Here. So in elastomers, what is the forces? Weak van der Waals forces are present. What is the weak van der Waals forces present in elastomers? This elastomer shows a property of elasticity. Okay, property of elasticity. So weak attractive force are present. Example, natural rubber. One example. Fibers, generally dipole attractions and the hydrogen bonded attractions are present. Hydrogen bonded. So example, sucrose, cellulose is one example for fibers. These attractive forces are fibers more than elastomers but less than thermoplastics. Thermoplastics, what is that? Weak attractive force are present, and thermoplastics, because of this attractive forces in not a proper way, this thermoplastics are becomes what is that? It is a fused. When it is heated, fused, and when it is pulled on again, it is formed again. So this is one example for we can use again and again. So weak attractive force are present in this thermoplastics. One example, polythene. Polythene is example for thermoplastics. Next is thermosetting plastics. Attractive force are very strong. They are very rigid with high melting and boiling points. Once these are fused, it forms a black color substance, cannot be regenerated again. Okay. Example, bakelite is one example for thermosetting plastics. Generally, bakelite is used in preparation of electric goods. So these electric goods can withstand high temperature conditions because of that what is a three-dimensional arrangement of monomer units, but it cannot be used again and again. Okay. These thermoplastics, some plastics after regeneration are soft, some plastics are not so soft, they are hard in nature. To convert thermoplastics into soft, we use some chemical substances which are called as plasticizers. To convert this thermosetting plastics into soft, we use plasticizers. Okay, based on decomposition properties, polymers are divided into two types: biodegradable, non-biodegradable polymers. Biodegradable polymers, which are decomposed in nature. This biodegradable polymers contains a hydrophilic groups. What type of group they contain? Hydrophilic group. They absorb water, decomposed in nature. Example, natural polymers. Example for biodegradable, non-biodegradable, which are not decomposed in nature. These are called as a non-biodegradable polymers, which are not decomposed in nature, which are called as a non-biodegradable polymers. Example, synthetic polymers are example for non-biodegradable, which contains hydrophobic groups. Okay, which repel water molecules that are called as a hydrophobic groups. Next, test for polymers. The polymer is obtained from animal, or that polymer is obtained from plants, or that polymer is obtained from what is that synthetic. If it is obtained from plants, how to identify that is obtained from plants? Use one test, that is called burning test. When polymer obtained from plants, it is in burning test, it gives the ash. What is it indicates? That polymer is okay, or that the monomer, that polymer is obtained from plants. If the polymer is obtained from animals, when it is heated in burning test, when it is ignited, it gives a burning skin smell. So this burning the skin smell indicates that polymer is obtained from animals. Synthetic polymers which are obtained, which are prepared in industries, it gives a black molten substance. Black color molten substance is obtained. So this indicates that the polymer is obtained from, that is prepared in laboratories, industries. So this is a burning test for polymers. So classification part completed. We discuss about a few important polymers. First we start with rubber. Rubber is obtained from rubber plant. Many varieties of rubber plants are there. One important plant is Hevia brazillus. This is one important rubber plant. From this rubber plant, natural rubber is obtained from, what is that? A white color semi-solid compound which is called latex. This latex contains isoprene units. What is this isoprene? 2-methyl 1,3-butadiene. What is this 2-methyl 1,3-butadiene? This is called as a isoprene unit. So CH2, CH3, cis, generally cis compound, CH double bond CH2. So n number of this 2-methyl 1,3-butadiene molecules are involved in polymerization, and it forms a natural polymer rubber So what is this? This is a structure CH2, CH, CH3, double bond, CH, CH2, like this, H, CH2, n number of molecules. This is the isoprene units which are involved in polymerization process. But what type of attractive forces are present? Weak attractive forces are present in this. So this rubber, natural rubber is, they show low tensile strength, low melting points. It is fused easily. To prevent this, we add sulfur. So that process is called as a vulcanization process. What is the temperature we maintain from? More than 390 Kelvin temperature if you maintain, then sulfur is added. So if we add a 2 to 3% of sulfur, okay, what is that? That is used in rubber bands, and 3 to 4%. It is used in tire industry. 50% if you add sulfur to this rubber, that is called as a, that is called ebonite. We can call hard rod-like substance is formed. That is called ebonite rod. So where this natural rubber is used after vulcanization process, it is used in tire industry. Main use of this tire industry, it is mainly used, and also shoe sole part of shoe and footwear also. This vulcanized rubber is used. Next, synthetic rubber. Next is synthetic rubber. What is this synthetic rubber? One example, neoprene rubber, Buna N rubber, Buna S rubber. Okay, Buna rubber. These are examples for synthetic rubbers. Okay, isoprene is the natural, neoprene is the synthetic. Generally, synthetic rubbers are used in footwear industry, tire industry, gaskets, and it is used in, what is that, engine lining. For engine lining also, these synthetic rubbers are used. Okay. Conveyor belts also, these synthetic rubbers are used. Conveyor belts also, the synthetic rubbers are used. What is the neoprene rubber? 2-chloro 1,3-butadiene. 2-chloro 1,3-butadiene is example for, what is that, monomer unit of neoprene rubber. N number of molecules combined, and it forms this polymer units. This polymer units, CH2, these are involved in polymerization process. So neoprene rubber, which is also called as a neoprene rubber. Next, what are monomer units in Buna N rubber? What is this Buna N rubber? Buna N rubber contains 1,3-butadiene plus acrylonitrile monomer units. 1,3-butadiene, CH2 double bond CH2, n number of molecules involved in polymerization with acrylonitrile, vinyl cyanide. Vinyl cyanide is called as a acrylonitrile. This both involved in addition polymerization. Buna S rubber. What is this Buna S rubber? N molecules of 1,3-butadiene involved in polymerization with styrene. What is styrene? C6, N number of C6H5, CH double bond CH2. This is called as the styrene. Buna is rubber. Buna rubber. Buna rubber. What is this? Buna rubber contains N number of 1,3-butadiene units. Here, these are what is that example for synthetic polymers. Okay, so we'll discuss in next class remaining on the polymers.